This meeting is being recorded.
In this video, we'll take a look at the next section from chapter 16 on acid-base equilibria. And here we're going to take a look at acid and base strength. So you should remember from previous discussions about acids and bases that strong acids or bases, they're called this strong terminology here because they completely dissociate or ionize in water. So whatever concentration you have of your strong acid or base, you'll have that after it ionizes. With weak acids and weak bases also, they only dissociate partially in water, maybe like 1 to 5% for most cases, for things that we call weak acids or bases. And their conjugate bases of these weak acids specifically will be weak bases. So conjugate bases are weak bases, etc. So what we have here, we have our strongest acids here give us the weakest basis. Our weak acids generate weak conjugate bases. And we can see this last relationship down here, that strong bases will give us weak conjugate acids. So remember those relationships when you're considering whether or not you have a strong acid or a weak acid or base, and you have to do some calculations to make sure that things are correct and you can rationalize your answers. So we should also note that whenever we have an acid-base reaction, the equilibrium will always favor whichever direction the reaction moves, so that the weaker acid and the weaker base will form. So we always move away from the stronger acid or base. So there's a couple examples here. The one on top we have with hydrochloric acid. That's showing us a strong acid here. And then we have this reaction below with a weak acid, acetic acid. So let's look at the strong acid here. It reacts with water, liquid water, that acts as a base. So our weaker acid in this case, we can take a look to confirm this at our table above. HCl is definitely a stronger acid than hydronium. So we're going to move towards the stronger away from the stronger acid towards the weaker. So we note that we move towards the right. So more products will be present at equilibrium than reactants in this case. When we have our weak acid here, our acetic acid compared to our hydronium, notice that now the hydronium will actually be the stronger of the two acids. So here's acetic down here, hydronium is stronger above. So we're going to move away from hydronium. So our equilibrium will shift to the left to give us more reactants than products at equilibrium. So we can move here to take a look at sample exercise 3. And we're asked to use the figure above to predict whether our equilibrium will lie to the left or to the right. So we also can state then will we have more products or reactants at equilibrium. So let's take a look at our first case here. So we have to compare acids to acids. So is this first species here acting as an acid or base? Will tell us whether or not water is acting as an acid or base. So this guy over here is receiving a proton, so it's acting as a base. So water will be our first acid to compare here to this conjugate acid. So let's take a look. Let's look at our table above. And if you recall, we have H2PO4 negative. So that's here, and water is down here. So it looks like this is our stronger acid. We're going to move away from our stronger acid. So we're going to shift left here, and we note that we're going to have more reactants than products at equilibrium. Let's take a look at this second example here. So who's acting as our acid, who's our base? So this is going to be our acid here that we'll compare. Hydroxides acting as a base. Water will be our conjugate acid that we'll compare. So we already located water, so we just need to find ammonium on our table above. So let's take a look. So ammonium is right here. So that's going to be stronger than water. So we're going to move away from that, right? We always move away. The equilibrium will always shift away from the stronger acid. So now we're going to shift right, and we will predict more products than reactants at equilibrium.